It's the language of the universe.
But I don't understand it.
Hello everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to another episode number 77, where today, for those viewers out there, you might be able to notice that we are in person.
We are living in the same apartment here in Toronto because the school year is starting soon. All of our classes are in person pretty much. So here we are. The podcasts from now on are going to be, live in the same room. We do have a new mic setup that we'll figure out soon. But we weren't able to get it running for today, so we're going to be using like this one mic. The audio quality is definitely going to get better
for sure
in the next episode probably. Yeah. So yeah,
a lot of exciting stuff ahead.
For sure.
A lot of exciting stuff.
Also, if you are watching on the YouTube channel, you can definitely see the merch that we are wearing right now.
Yep.
Little disclaimer, we are not selling them yet. We just made 2 of them while we were like in the process of doing the giveaway. We're like, okay, well, might as well make 2 just so we can wear them around because, excellent merch here.
Excellent merch here. And I believe our merch winner is also Tejaswini getting her merch probably this week, actually, because I believe we sent it out recently. So that's going to be coming to you probably, hopefully before the episode drops. Probably not, but if it does, congratulations and keep participating.
Yeah, and just know we wanted like high quality merch, so everything is embroidered. It's not like cheap printed or anything. It's all embroidered, all high quality. We're going to have to spend a little bit of money, get a website going to sell the merch and all that. It will come 2022. Definitely.
2022.
2022.
I mean, it's September. Yeah, 2022, the website will be up and running for sure. We'll have a merch, a store, hopefully. Oh, that's going to be so cool. I'm already so excited about what's going to happen. But I think we're very excited. I think we're too excited right now. But it'll definitely happen. So if you're excited about these shirts, and if you're listening to us, hop on YouTube right now. And
go like the video while you're here.
Like the video and see the merch.
And also follow us wherever you're listening to this, but especially if you're on YouTube, leave a comment. Because every single week, we pick out a comment as the comment of the week. And this week's comment comes from Mr. Alexei.
Ooh.
He says, "Thank you so much for your hard work and dedication. I'm a mobile detailer, and I'm constantly finding myself daydreaming about the fascinating world of physics and mathematics, listening to you guys while I work. I especially love your history episodes. You guys make these topics so interesting and laid back, relaxed, and conversational style rather than a classroom lecture." Yeah.
Wow. I mean, that is our intention with every episode, right? We are trying to keep it conversation. We're always trying to, but also kind of educational because we're in the field and we're trying to learn more every day. And, so many times when I mention this so much, but every time before we record a podcast in the quick segment where we do our research, we learn so much about whatever we have. So great props to that comment. Thank you.
100%.
Yeah.
In terms of news, I think we are almost at 14,000 followers on Spotify.
Wow. That's
pretty close.
That is pretty close.
I gotta say. Spotify has always been killing it.
Yeah, Spotify's been doing well. So thank you to everyone who continues to listen there. Google, our podcast platforms are going going up for sure. Apple Podcasts is really nowhere. It's really nowhere.
They don't have a good analytics section.
I think so. But anyways, we also recently hit 215,000 downloads, so that's also a sort of a milestone. But our 250 is soon.
Yeah.
So definitely watch out for that.
Almost a quarter million.
A quarter million. That's going to be big.
For sure.
Yeah.
Definitely excited for the milli. That's going to be a big moment. All right. Today we're bringing back a topic that we talked about a very long time ago. And we did 3 episodes. It was an astronomy episode. We talked about a lot of things like calculating the distance to the moon, calculating the radius of the Earth. Like, how do you even do that, right? It kind of trips you out if you think about it for 2 seconds. Also, things like tidal locking. We did talk about types of stars, but today we're going to get like more in depth into the actual life cycle of stars themselves. Go through from the beginning all the way to the end, and then what is the universe tending to in the limit as time goes to infinity.
What will happen to stars, right? Like, what will happen to our night sky? So I think, today we're just going to go over a little bit more in depth onto the star itself, the star's life, right? Stellar evolution.
Definitely an interesting topic. You know, in astronomy, in astrophysics, you would think like, okay, you study stars, galaxies, the universe, and planets. Each one of those topics has so many things to discover. You know what I mean? And so stars being the major components, quote unquote, ignoring dark matter and dark energy, but
matter.
When you
major component of matter.
When you look into the sky, you see stars, and so obviously humans at some point were like, okay, we gotta, like, what are these? And just know, no human has ever been close to a star. You know, we can't just go up to a star and study it like you would a rock or something.
But the advantage of a star is that it radiates. I mean, that's a big thing about it, right? That's the fundamental concept. And with that radiation, right, we can deduce things about the star. And that's mainly where everything comes from, right? Because a lot of science, we don't actually have the information at our hand. We're just assuming, we're making assumptions, we're making deductions. Sorry, that's the better word. Like, the classic example is how Einstein literally discovered the speed of light with no idea, like, where to even start, right? So just like in a similar way, you can think of stars, like, because where do you even start? You're looking at some things. Do you start with a telescope? Well, that is how we started.
Well, no, but people actually in like the 400 BC era, I think it was Hipparchus that was classifying stars based on their brightness to the naked eye. That was like the first classification that you could even make, right? What else are you going to classify? All you can do is look up at the sky. You're going to say, some of these are brighter, some of these are dimmer. We can kind of, and that's actually how the magnitude scale came up. Like, why is it that the magnitude scale is so weird? One, like, a difference in one unit of magnitude is like times 2.05 or something like that. This might be way off, but usually when you have like a logarithmic scale, it's like base 10, but this base is like base 2 point something.
2 point something. I think
it's because it was made with the naked eye, and we kept it. So
that's crazy that we actually ended up keeping it, because usually with science, when technology advances, we also advance in our measurements. But it's interesting that is not actually what happened.
I mean, it's bad. It's like using the imperial system, but it's not the end of the world, you know. If all we're talking about is magnitudes of stars, we can deal with it.
Because with magnitudes, right, there are two major things. There's your relative and there's your absolute. Yeah. Now, relative, if you think about it, is not crazy important to really have a well-defined system, because it's relative. If you're saying this is brighter than this, no matter how you define both of them, if one is brighter, it'll still be brighter. Yeah. So there's that system. And the absolute system, okay, I guess you can maybe think of a better way to do it now that we're here, but I guess it's just tradition that we're using it. Yeah. Right? So we're just continuing.
Yeah, by the way, the absolute magnitude is the brightness of the star, or the magnitude of the star, from 10 parsecs away. So when you classify the absolute magnitude of a star, it's the same for every star.
Yeah.
What's that word? It's like standardized.
Standardized. It is standardized, which is also and that is really where we compare your luminosity, your brightness, and factors about these stars. Because relative can only tell us so much. Because where one, rock floating around in this gigantic soup of the universe.
Yep.
And everything that we're seeing, everything like relative to us, doesn't really matter, right? Because the universe will continue to exist. It doesn't care about us. So that is also why the relative nature, it's important when we're comparing two things. But if you're simply, again, deducing facts about the star, that's where absolute comes into hand.
100%.
Right? We can use a lot of that.
So
also, I do want to mention, because I just thought of this before we really dive deep. The listeners, the viewers may very clearly already noticed that my voice is a little bit under the weather. I mean, I am a little bit under the weather for this current episode, but still pulling through for this episode to drop on Monday as usual. So we're just going to continue with that, but I had to mention it because I was just thinking about it.
yeah, and it's also 11 p.m. before the Monday that we
They don't know that, though. They don't know that.
I'm just saying it's late, but whatever.
Yeah, it is a little bit late. It is on... Definitely, we could have thought about this a little bit more, but here we are, very excited, as always. Let's get back on.
So, let's get started. Let's talk about the very beginning.
How it all started.
We already talked about the Big Bang.
We did.
We made a whole episode on the Big Bang. But now, getting deeper into the actual topic of stars, we should start with density fluctuations in the early stages of the universe. So
matter density.
Yeah, matter
density. Because do remember in this big... Oh, no, so I think we've definitely mentioned the Big Bang singularity, or the initial singularity is kind of what it's called. So in that initial state, well, we have no idea what actually was going down. We have a estimate that, hey, there's a ball of energy that has something in it. Lots of things in it. Now we know that those things are mainly categorized of matter, dark matter, and then dark energy. How and where it got in there, who knows? But that's what we kind of know from our all deductions of CMB and everything. And then from there we say, okay, well, how does this singularity, because remember, a singularity, if you think, like, even if you think of a ball of energy, you're still thinking about some kind of volume that it takes up. But this is a singularity. This is a zero-dimensional point and space doesn't even exist yet, right? So there's, you can't even imagine this. I love keep continuously talking about this. It's like a point in nothing. When you think of space, you think of nothing, but nothing is space. So technically that's, you know what I mean? So it's always a little hard to really perceive what was happening. I mean, no one really can. But the best idea that we have is that, hey, we had some, what we like to call quantum fluctuations that were happening in this singularity. Now, why? Quantum fluctuations happen everywhere. We've spoken about this, I believe, in a few other episodes, where it's basically virtual particles that can pop in and out of existence. Now, the reason why that can happen is because of a very simple fundamental physics concept called the Heisenberg's uncertainty principle. Again, things we've already discussed before. And that's the fundamental idea of a fluctuation. Why it comes up, again, definitely go check it out. But why it comes up is basically as simple as two particles pop into existence. So they borrowed some energy from the universe. That's the easy analogy. And then it has to give it back. However, if there is this point and there are all these fluctuations happening back and forth, because a particle, if you think about it, is also a point-like particle, these virtual particles. So if these point-like processes are happening in this point-like space, and it happens a lot, things start to move. Things start to move.
So now, a slight increment in time after the Big Bang, you could imagine the universe is this small sphere packed with everything that is now everywhere, right? To keep it simple. And in this small sphere, you can you can cut it open like an apple.
Okay.
And look at the matter that's inside. You take a snapshot of the early universe, and you still have this push and pull between the matter that is inside this ball that we know as the universe. And with this push and pull, you're going to have very small areas that have slightly more or a slightly higher density of matter, and some areas that have slightly less density. And we like to use the balloon analogy.
Balloon
Imagine
analogy.
you have a small balloon.
No, it's like completely deflated.
Yeah, no, that's what I mean. That's what I mean.
Yeah.
Your balloon is deflated, and the areas that have high density, you draw like dots on it, right? And those dots are relatively close together.
Mm-hmm.
But when you blow up that balloon to the size of the universe,
Mm-hmm.
the distance between those dots expands very, very much, and you're left with these pockets on the balloon that have higher densities than the neighboring areas. And those areas in the universe are actually where you find galaxy clusters, where galaxies are formed, and in galaxies there are stars that are formed.
Mm-hmm.
And so now how do stars even get formed? So we know that when you want a star, you need mass, right? You're not going to see stars being made just where there's nothing. You need something. In the early universe, there weren't stars. There was a point where stars weren't a thing. There was just this soup of matter. And so now, fast forward, where the universe is expanding, and now you have these pockets of higher density areas in the universe. And those high density areas start off as just clouds. Because the early universe, you just have, protons, neutrons, electrons, which...
No. Neutrons came later.
Sure.
For protons and electrons.
Yeah. Sorry, you're right. So you have protons and electrons floating around. Mm-hmm. Eventually, those turn into hydrogen atoms. Hydrogen atoms are 1 and 1, right?
Simple as that.
Now you have these gas clouds. Mm-hmm. And these high density areas in the universe were due to these clouds of just helium. Oh, I keep saying helium. It's hydrogen. It's just hydrogen floating around. Mm-hmm. And at this point in time, the force of gravity, quote unquote, okay. the force of gravity has been separated, right, from the 4 fundamental forces. It was the last to separate. But now that...
You want to take that route? Because
no.
Because
I was just
force, maybe don't get into the force thing, because
But now you have the force of gravity, and even though gas clouds, you wouldn't really, if you have a box filled with air, you don't really consider the gravitational effects that the particles have on each other, because they just seem to float around. But over time, if you take a gas cloud that has an incredible amount of mass, because there's an incredible amount of hydrogen in the air, you let time do its thing, and gravity will slowly but surely pull these hydrogen atoms closer and closer together. And now, these clouds are absolutely gigantic. Mm-hmm. And so, what happens is that these atoms that are floating in space start to get crushed closer and closer together. And then gravity doesn't stop, it just keeps pulling things in towards, let's say, the center of mass of this gas cloud we're talking about. And, atoms are, I don't want to say, I was going to say indestructible. No, I was going to say they're not indestructible. In the sense that there are forces repulsing atoms from each other. Just like I can touch Rayhan and I won't just go through him, right? Mm-hmm. There's some repulsion there.
Electron repulsion. Yeah.
But imagine if I were to push Rayhan with such an incredible force that the literal atoms in my body start to counteract that repulsive force, and our atoms start literally touching. And what happens at that point is that in the case of the star, we have fusion. The nuclear fusion of hydrogen atoms.
Nucleosynthesis.
Yeah.
Stellar nucleosynthesis.
Yeah. So in these gas clouds, the hydrogen atoms are literally getting pushed together so much that they turn into helium. Before we didn't have helium. There was just hydrogen, because helium, you don't just find it.
Yep.
In the beginning, you don't just find it. It had to be created through nuclear fusion. So, yeah.
Well, all of these processes have a very fundamental concept, which is all elements nothing really existed at that time. Because at that time, the only thing was these protons and electrons. We happened to call a combination of one proton and one electron, a hydrogen atom.
Yeah.
So it just happens to be that.
Yeah.
But, well, the exact thing is not one hydrogen. The exact thing is, well, there are 4 hydrogen atoms actually that come together to make one helium-4 atom, which is actually technically what happens, right? Which is where it's the same thing. I mean, it is the same thing, but the power released by that particular process is what fuels what then becomes a star. Mm-hmm. But we're not there yet, because we're still at like the protostar phase. Like we're still at nothing is still formed yet. So when it's still a cloud, of gas, right? Again, a cloud of gas, when we say gas, again, you're really imagining steam, but steam is not really hydrogen, right? Because you can't really see anything. So what's actually happening is these guys are just collapsing under each other. But then you may have a question, what are the requirements for said gas cloud to collapse? And that's also something really interesting called the Jeans mass. The Jeans mass is the minimum mass for a gas cloud, to collapse into a star, right? And all gas clouds, like the way stars form, is from gas cloud to star, but it's not direct. In the middle there's a protostar phase. And in that middle ground is where the star is not really a star, but there's some gas that has been concentrated, some fusion happening, but there's still a lot of gas around. So in this particular phase, very similar to the formation of our solar system, actually, the protostar. So how it works is when gravity is crushing everything. Remember, things are very hot. You're talking about millions and millions. Okay, I can't even say kilograms because this is like astrophysics scale, right? Lots of mass basically coming together and heating up to a very, very, very high level. And in the middle, where the gravity is contracting everything to, again, if we're not looking at the force of gravity, you can even think about the general relativity way. If there's enough mass somewhere, it creates a depression in space, so then all the other gas continues to fall there. So as it's falling, we have the middle that gets really, really, really hot, which then turns into usually a star. But in the beginning, it's still a protostar. And in that particular phase, the outside of this particular cloud, lots of things can happen. More of the mass can start coming into it and make an even bigger star. Or, similar to what happened to us in our solar system, the outermost layers of the gas, if the gas cloud is too big, not massive enough for these big stars, it starts to cool down. Cools down into rocks that we now live on.
And
that was a nice one.
But also what can happen is that if there's not enough mass, it's that when hydrogen starts to fuse, what'll happen is that the radiation will actually knock the gas out into space and the star will never actually form.
Yep.
That's the Jeans mass, right? Because if it's not massive enough, the star won't actually form, the gas cloud won't actually fully collapse. And there you go. So, now that we have a star, there are a couple classifications.
Before we continue into the classifications of the star, just continuing on the requirements for the star to be even existent, is one of the very most fundamental concepts in stellar astronomy. And that is hydrostatic equilibrium, or equilibrium in general, right? For anything in the universe to occur, I wouldn't say to occur, but in general, equilibrium is an attainable source. Usually everything tends to equilibrium, is what I'm trying to say, basically. So hydrostatic equilibrium is basically a way of saying, hey, every star or every mass, as we were just talking about, has some gravitational pull on there. Again, if you're thinking about general relativity, has a depression. So you can always make the relation between the two, but you know what I mean when I say force. So every star, every mass has some force of gravity pressing it down, right? However, for, again, this star to be in equilibrium, for the star to actually exist, so there just has to be something counteracting this gravity. And there are two major things, right? We have radiation pressure, which is one. And is that the major thing?
Yeah,
that's just the major thing. So because of these nuclear reactions happening in the core, what happens is there's a lot of energy that is released in the opposite direction to gravity, right? Because what's happening is as you start packing more and more down here, it starts producing more and more energy, which is allowing the star to resist the collapse of gravity. And when it reaches this nice tone where the force of gravity and the radiation pressure are equal, we call it hydrostatic equilibrium. And that is when the star is truly formed, right? Because a lot of things can happen where the star will always tend to equilibrium, always. So if it's too big, you know what I mean? Like the volume is too heavy, then it will try to get smaller. If it's too small, it'll try to get bigger, try to counter both of those and try to keep them equal, which will always try to happen if it has enough mass to form in the first place, right? Which is kind of like a fundamental, how do stars form, or what are the requirements for a star to form, at least one of them.
Yeah, so now we have stars, but over time, in the beginning, you would look into the sky and you would see stars, and you could assume that they're all pretty much the same, right? Some of them you can kind of see the color of it is a little bit different, but you would assume that they are pretty much the same. As technology got better and better, we started discovering that there are clear categories of stars, and they differ from each other. And the thing is, we can't see stars evolve. We can see certain steps, for example, like a supernova, which we'll talk about. But when a star is in one of its phases, we'll usually never, right? Because the process is so slow that if we see a star, for example, that's on the main sequence, which we will get into in 2 seconds, if a star is in the main sequence, that star will always be in the main sequence for our lifetime and probably the lifetime of the entire human civilization. And so it took a little bit of connecting the dots and maybe evolving the theory of the life cycle of a star to really put together these branches that I'll mention right now. So first of all, when a star is properly formed in, hydrostatic equilibrium, it's burning hydrogen in its core. That kind of star is on the main sequence, and the main sequence is actually the longest state that a star will be in
ever.
Because in this state, the star is completely made of hydrogen, and so when you're burning hydrogen, you will be right. The oven will be on for a long time. As soon as you run out of hydrogen, things start changing very quickly relative to the main sequence, and then you will evolve into something else. But here we go. Hydrogen turns into helium only in high pressure areas. So we're talking the core, where there's the most amount of pressure. So you can kind of imagine the core of a star is just this ball of helium that is slowly getting bigger and bigger because it's continuously fusing hydrogen into helium. I don't want to mess that up. And of course, it does take even more pressure to then go from helium to other elements. But
we'll get to in a bit.
Right, in the main sequence, you're just building up that core of helium, and then around that core, you'll have like a sphere of hydrogen being turned into helium. That core will get bigger and bigger over time. Our sun is in the main sequence right now, and most stars are in the main sequence. One thing that's really important is the Hertzsprung-Russell diagram, which was created just by looking at stars, their properties like the size, the temperature, and the luminosity. And you can clearly see the main sequence on this diagram. I'm not going to explain what it looks like, but there are branches, right? You can see the branches of stars that are in the main sequence. And then after the main sequence, you can see different paths that stars take. Now, there are such things as low mass stars.
Have we explained the main sequence though, like at all, like HR diagram?
Well, it's when hydrogen is burning.
Okay, I don't know, but like I was just talking about, like, well, the whole premise of a main sequence is, well, first off, what is it? Like, it's put on a diagram that relates temperature to luminosity, Now, these are very, very, very integral parts of stars, because with these two relationships, we actually see stars on the main sequence follow a proportionality scheme. Basically, the bigger they are, the more luminous they are. And there's a relationship between temperature, not more massive. I meant more temperature, or the hotter that they get, basically, the more luminous that they can get. And this is kind of where we also see on the main sequence, it's actually a line. If you see the stars on a main sequence, it's basically
kind of linear.
It's kind of.
Yeah.
It's not exactly, of course. Nothing is really exact in the world, but it's kind of simulating a linear progression, which tells us something about these stars, right? And stars can spend, our sun, for example, will spend 10 billion years on the main sequence.
It's already halfway through, but
10 billion years on the main sequence. And the number one factor that categorizes how long a star will stay on the main sequence, or how long a star will burn its hydrogen to helium or whatever, is its mass.
Because the more massive you are, the more hydrogen you have. Automatically.
Exactly. The more hydrogen you have, the more hydrogen you burn. The more hydrogen you burn, the faster you burn. Right? And now the problem, or not the problem, but usually what happens, or what always happens with these much, much, much bigger stars is, do remember, bigger stars also means bigger gravity, also means bigger pressure that they have to now form. So again, even though it may seem like, oh, they have more hydrogen, why can't they last as long? But the gravity is also a lot higher. A lot higher than they have to counteract.
Just know you need a certain amount of pressure to actually fuse the hydrogen into helium. And once you pass that threshold, you're fusing it, right? So if you have a high mass star, you have a lot more pressure. The pressure is going to be the highest in the very center, and the pressure is going to decrease as you go outwards. But if the pressure threshold for a very high mass star goes, a little bit further out, you know what I mean? So in that entire area in the core, you're going to be fusing. Yeah. Right? Versus a lower mass star, where that radius, that threshold, is going to be smaller, and automatically the amount of fusion happening is going to be less, and you're going to last longer of that.
And interesting fact here, our sun, as I mentioned, 10 billion years on the main sequence. But a star 10 times massive as the sun, which is not that uncommon to find out, by the way. 10 times as massive is relatively common in stars, because our sun is not a very big one. So a star just 10 times more massive than our sun will last only 20 million years on the main sequence. Significantly less than your 10 billion, which shows you basically the relationship between how important your mass is basically for a star to be on the main sequence. And that completely dictates its branch on the main sequence, right? The mass of the star will determine where it goes, what's going to happen to it, and we're going to get into that right now, I think.
Yeah, so there are two branches, low mass and high mass. For a low mass star, like our sun, for example, once the hydrogen gets completely burned up, then there are a couple of options. Actually, no, wait, sorry. The options are in between the high mass and low mass stars. So, the nuclear reactions, as we talked about, as the core starts to grow, the nuclear reactions start to get pushed near the outskirts of the star. And so what happens is that the atmosphere of the star actually cools down, and the star starts to get bigger.
Then this is, again, because the core is already fused. The core is, remember, right now at this stage, now what we're continuing on to, the core is already fused. The core is helium. We don't have enough pressure right now to fuse helium and anything else. So right now, the only two elements that exist in the universe are hydrogen and helium. Or at least in this very, very basic universe that we're starting with one star. Right? Because usually a lot more processes happen while stars form as well. So there's a lot of extra stuff happening on the side. But for now, in this scenario universe, we're going to continue with this just one star. Yeah.
So this phase is called the red giant phase, because your star starts to expand, I guess, quickly.
Very quickly.
I don't know if that's relatively.
Again, it's all like even when you said short a few times back, even that it's all relative, right? Like even like when you say short, in astrophysics terms, that's a couple 100,000 years, is what we're saying. So that's still quite a long time for us,
For sure.
right, when we're comparing that. And the red giant phase, again, is simply because when that core is already fused, the outside hydrogen is like, what do? We don't have a center to stick to anymore because we can't fuse anything in there. So what they start doing is that they start now repelling each other because they have nowhere to go. So they start basically expanding in this outer layer that we like to call a planetary nebula in this case, or in the red giant phase. We're sticking with small mass right now, by the way. So in the small mass timeline, when it hits that red giant phase, what basically happens is, again, core is already fused, so the outer layers simply start to expand due to the gravity. Because remember, the core is done,
right?
So there's no more else that they can do.
The pressure is, instead of, the gravity is not strong enough to hold in the outer layer, and so the pressure actually just radiates this outer layer, and it's actually pretty colorful. If you search up planetary nebulae, it's like this colorful thing in the sky, and that's actually just the outer layer of gas of the star just going out into space. And what's actually left, now that you have just the core that's left, right? The core, let's say, that turns into a white dwarf. And a white dwarf is pretty much trapped, because for a low mass star, that's where you go to die if you're a white dwarf. So what actually holds up a white dwarf is no longer just pressure from, or radiation pressure. It's not neutron degeneration. It's electron degeneracy pressure for the white dwarf.
For the white dwarfs.
Yeah.
For the white dwarfs.
And for the...
That would be neutron.
For the neutron star, yeah.
Right. So degeneracy pressure is basically a simple electrostatic term, where it's like two light charges, again, will not want to go in the same spot, so they will want to repel each other. And when gravity is not crazy and is not doing anything too nuts, these guys can repel each other very easily. Right. So that kind of what happens, that end up happening. And most of these white dwarfs are usually helium, and they're a lot smaller. Right, so after those outer layers have been shed, we now have this core that could be shrinking. Now, in this particular stage, there are also some things that can happen, because a white dwarf, I guess, no, not by itself. It can't.
On its own, it can't.
It can't by itself. It would need something else, right? So by itself, I guess it's kind of dormant, because that would be the last stage. For example, our sun will go through a white dwarf phase right after it passes, because that planetary nebula will basically engulf everything until Mars.
Well, no, the red giant.
I mean, sorry. The red giant. Well, yeah, you're right. Yeah, the red giant will basically engulf everything up until Mars. So our timeline to leave this solar system is about 4 billion years. It's not terrible. It's not terrible.
We got time.
We got time.
But what happens, as you know, mass is equal to energy divided by c squared, if we want to remix the equation. And obviously a white dwarf is still radiating some type of energy because we can see it, so that's a little indication. But it's not doing anything. It's just sitting there and radiating. So over time, you're just going to lose the ability to radiate, because you're just going to run out. And that's when the star will actually just die. It'll just cool down and just die.
Well, no, not immediately, because white dwarf turns into brown dwarf. So white dwarf is still, remember, whenever you hear any color, okay, that's not actually true. In astrophysics, brown means no light, is a nice way to think about it. Because brown is not a color in astrophysics. It's just not a color, right? Brown is a color that we have made, but brown is not really a color. When we say white, it means all the colors. So when we say white dwarf, as you just mentioned, Barker, the star is still radiating something. We can still see this particular thing. But in the situation where it kind of runs out, if it's just chilling there, nothing is really happening on the side, then yes, it will simply continue to radiate. Gravity continues to basically try to take it down, but it has nothing to really do. And then the light basically simply just turns off. And it's a very sad way to go. It's nothing too fun to really watch. But that's one of the stages of what will happen in this particular situation.
Yeah, for high mass stars, it's a little bit different. It's actually a lot different.
It's a lot different.
It goes into a stage that's called super red giants, and it's similar to the red giants, but it's obviously there's more mass, and so the core is actually able to continue to burn helium into other elements, and then other elements into other elements, and so it lasts a little bit longer. Actually, that's not.
But what actually does end up happening is because in very, very massive stars, again, when the helium when the hydrogen is run out and there's that core of helium in the middle. Remember, these are very massive stars, so there's a lot of helium in this middle. So what actually ends up happening in these supergiant phases is the very outer layers when they start to expand, there is still enough mass in that helium itself for more stuff to happen. Because when the star is so big, taking up that volume with a lot of hydrogen there, not much happens. So that simply dissipates. But when it's concentrated into the helium over a smaller volume as well, nucleosynthesis starts to kickstart again. And now we have a whole new trajectory, which is really where you see all your stellar remnants, all your big things in the universe, you really see in the second massive stage, right? And after this particular situation where there's a helium core, it simply continues. Helium, now there is enough pressure, because again, gravity, it's all about gravity. The gravitational pressure on the star is so heavy that the core of helium itself starts to refuse, right? They continue to fuse. So helium goes to carbon, and then it just continues because, again, it's a lot more massive, so it has enough pressure, radiation pressure, or not radiation pressure, but enough gravity to cause the nucleosynthesis. And it continues on until we finally get to iron. Now, iron is a big problem because iron requires a lot of fusion or a lot of energy to fuse. And even in gigantic stars, it's not a thing. There's not enough energy for iron to fuse. So iron is kind of the last stage. So if you search up, in a lot of people ever interested in astronomy may have done this, where you search up like those big stars and you see hydrogen, helium, carbon, like you see those rings going to the very center, and in the center, always iron. Because that's where it stops. When there's iron at the center, again, when the core is not running, the star doesn't run. Because they're like, what do we do? The core is where there's the most pressure.
Yeah.
So if that guy isn't running, the star is just not running.
Yeah. And when you turn off the oven, the power oven, you turn it off, you stop fusing, all of a sudden the pressure drops.
Yep.
And now, we talked about hydrostatic equilibrium. You turn off the opposing force, we get something called a core collapse. Ooh. Supernova. The core collapses in on itself, and you get an explosion. It explodes, and a couple things can happen. One, you can either turn into a neutron star, which is actually the most, apart from black holes, the most dense object in the universe.
Yeah, I thought you were going to say common, but yeah.
No, the most dense object, and it rotates very quickly because obviously stars rotate, and then due to the conservation of angular momentum, you become a smaller thing, so you rotate faster. Neutron stars are supported by neutron degeneracy pressure. We should...
No, for sure, we're definitely gonna get it. But okay. I'm just saying before. I mean, okay, I guess we can. Because neutron stars in this. So one thing I just want to mention before the neutron star phase, when there's iron in the core. Again, sorry, a little backtrack here. But when there's iron in the core and this thing wants to basically explode, what's happening is the center again can't do anything. It can't fuse. So while the rest, the outer layers are like, hey, can we do anything? Iron's like, nah, we're not doing anything. So what actually happens is, because do remember, the sun and, not the sun, but all stars aren't really, it's not a solid object. Like you may be thinking of a sphere and they're all like the whole thing is connected. That's just not true. They're all like separate. It's literally elements separating each other. So when the iron can't fuse, what basically happens is there's enough iron in the core that the core, because I think when you say core collapse, you may have kind of given the idea that the star collapses, but the actual thing is that only the iron core actually collapses, which then basically causes this effect. But what ends up happening, and this is really cool, and I think I did mention this before, shock waves. So when the iron core collapses, it basically, again, it does explode, which causes shock waves to basically reverberate at the core. So it leaves and it comes back because it's so powerful. And this particular explosion, which we call a supernova, a type 2 supernova, we'll get into the other one in a second. But in this particular explosion, we have oh wait, I forgot what I was talking about. It's complete brain glitch sometimes. No, I was talking about supernova, but what I was trying to say is in this particular explosion, the energy is so powerful that the shock wave forces the iron to fuse into heavier elements. And this is the only place that we get iron fusing into heavier elements. Now, what does it fuse into? It fuses into things like platinum, things like silver, things like gold. And I always love to tell this fact to anyone who doesn't know something about astronomy. If you have a gold chain, a gold anything, well, technically even we're stardust at the end of the day, because we're carbon beings and carbon is from stars at the end of the day. But if you do happen to really go and think about it, even that gold chain or whatever that you're wearing right now was caused and is on you right now because of some crazy explosion, a crazy supernova that blasted gold into all directions. Some gold ended up on the earth. We mined it. It's on your chest.
Yep.
Right. So the whole process of this iron fusing into heavier elements, because we need it to occur for heavier elements, because all the elements in our universe are created this way. Right? We can make elements now in the lab and stuff. That's different. But naturally, of course, this is the only way that it can happen, because how else are we going to create heavier and heavier elements without this pressure?
With Paul Delaney, we talked about primordial elements that can't be created, right?
Oh, like boron. Yes, I do remember that actually.
Yeah.
Oh yeah.
And I don't really know anything about that.
Yeah, we don't.
So.
I don't think we can talk about that. But that's there was a primordial element thing.
No, there's a couple. Like there
were a couple.
There's a list. But yeah, let's talk about the type. Let's talk about the type 1A supernova. So remember when we talked about white dwarfs? We said that there's nothing that can really happen. They just die off. Well, there are things called binary systems where you have two stars orbiting each other, or the common center of mass. And usually we see that there's a white dwarf and then a main sequence star next to it, and they're orbiting each other. What happens is that the white dwarf undergoes a process called mass accretion. What happens, and this is one of like the coolest images that you can get of like space things. What happens is that it literally sucks mass out of the partner star into the white dwarf, and it literally looks like a funnel that goes around into the white dwarf. And so now here's the thing: white dwarfs are very, very hot, very, very dense. Without another star beside it, nothing can happen. But as soon as you start supplying extra mass, you can actually have a collapse as well. Because now you're pumping extra mass, you're giving it more, a higher force of gravity. But remember, a white dwarf is supported by electron degeneracy pressure, which does have a threshold. That threshold can't be crossed with just the white dwarf itself. As soon as you start adding mass, the electron degeneracy pressure is battling the increasing force of gravity, constantly increasing because of that supply from the other star. Now, once you do pass that threshold, the white dwarf collapses and undergoes a type 1A supernova.
Well, in some situations, though, a white dwarf can also reignite. Right.
Oh, I don't know.
Right. So in I believe, isn't it?
I don't know.
Okay. Well, I don't want to speak inconsistently, but I believe there are some situations where a white dwarf can reignite its fuel because of the mass supplied from a neighboring star. So the supernova happens when there's a lot of mass accreted and it simply explodes. But if there's, I mean, again, there's definitely a threshold of mass for it to be accreted. And if that, I'm assuming that threshold is accreted, the gravity will start to push it down. And again, if it's at that threshold, what, again, just in my head, what should happen is it should reignite, right? Because if you think about it, it's a ball of helium. What does a ball of helium need to ignite in a big star? Mass. It gets more mass. Simple assumption is that it should reignite, right? And that's a crazy, and that's type 1 supernova. A little sidetrack for the supernova, but that's one way that the white dwarf can also reignite or just basically explode. And getting back on that neutron star, because I know we were talking about neutron degeneracy pressure and stuff like that, very similar to electron degeneracy pressure. So in a neutron star, this is crazy, and I believe we have mentioned this before, but in a neutron star, the gravity is so immense that nearly 90% of the star's protons and electrons fuse to make neutron, right? So the neutron star is only 10% protons. It's not all neutrons, which is a common myth, because remember, neutron stars have very, very powerful magnetic field. How can it do that if it's only neutrons, right? So anyway, so they do have a small amount of protons and electrons, which do cause the fields and everything. But the star itself is a bunch of very, very tightly packed neutrons, to the point where they can't go any deeper or any closer because of simple electrostatics. Because they're two, well, not charges, I guess neutrons aren't charged, but well, they're two particles that are simply repelling each other because of the fact that they have the same charge. Right? So that pressure basically is what allows neutrons or neutron stars to continue. And a crazy fact is that a neutron star can be 2 times as massive as our sun. It's our sun. The size of Manhattan. Size of Manhattan.
Very
I think it's a pretty popular picture. Again, if you've searched up neutron star pictures, if you've ever presented on anything like this, then you definitely see that Manhattan picture. It's literally Manhattan that they compare the neutron star to. 20 kilometers in diameter. 30 kilometers in diameter. And 2 times the mass of our sun. That is the pressure that is. And imagine the amount of pressure that these neutrons have to hold up, because the gravity on this object will be immense. Immense gravity. And it has to hold that up simply because of neutrons.
Yeah. And now,
right?
Now you have these white dwarfs that can collapse into neutron stars. You can also have we went from neutrons. Oh yeah. So the high mass stars collapse into neutron stars. They can also, I think, collapse directly into black holes.
If it's really massive.
If it's big enough.
If it's really, really massive, what basically happened is, so right after that supernova, the remnant is one of 2 things. It's either a neutron star or a black hole. And that is completely dependent. Or actually, it can also be a neutron star that then turns into a black hole, which also actually does happen quite often. But again, that would require extra mass and stuff from here and there, not by itself. But if the star is really, really, really massive, what happens is, while this thing is crushing the protons and electrons and all this stuff into these neutrons, the gravity is so immense that even neutrons can't really keep up with what's actually happening. And I mean, then we just know the classic story. It basically simply collapses onto itself, and there is a space of nothing.
Turns into a black hole. We talked about episode 43.
Mm-hmm. Oh, you remember the episode number?
Wow. No, don't quote me on the episode number. I think it's in the 40s though. We have a whole episode on black holes.
Mm-hmm. Called Black Hole, actually, all in caps. It's a pretty cool episode that we go very deep into black holes about, but yeah.
So yeah, as the universe ages a lot, stars, like star formation in the universe has slowed down significantly. Right now, we are not producing, like, I think a galaxy produces like 3 or 4 stars a year. I think that was the figure. Like, it's not as much as you would think. And I remember, I think we were in class, and that was one of the questions where it's like, oh, how many stars do you think a galaxy produces? And I was like, oh, maybe like 10,000 per year.
10,000 is a good. No. 10,000 is a good estimate, which is what we thought.
No, it was completely wrong. It's literally like 3 stars. And remember, some galaxies don't even make stars, like elliptical galaxies. Star formation is maybe not. Don't say. I shouldn't say they don't produce stars. Like, I'm sure there's a counterexample, but usually it's spiral galaxies that have lots of active star formation. But nowadays that's slowed down, and as stars start to age, stars will be, evolving, and near the end of the universe, we're just gonna have dead white dwarves and black holes floating around, and black holes evaporate very slowly near the very, very, very end of the universe, which we don't know about the whole Big Crunch thing, but let's assume that the universe is just expanding forever. We will just have this soup of atoms. We'll go back to this black state of just equilibrium in the entire universe.
That would be very bleak.
Bleak, but maybe, I think we don't have enough information to really know what happens at that point. Like for example, like, what if, when you think of the singularity, you think about like a bleak point. You know what I mean? Yeah. It's a bleak point. Yeah. But what if, when our universe just dies off, heat death, right? What if the size of our universe when we reach that heat death is actually it's the size of a singularity in a bigger, and then once we start seeing these fluctuations in our eyes, they would be like, what's the word for large? I don't want to say classical. Yeah, I'm talking about, like fluctuations, but if you zoom out, they would look like quantum fluctuations in the bigger perspective. This is all. Yeah, this is all off the books. Right?
Yeah. No, for sure. But yeah, that would be but I mean, who knows? That could.
I mean, these are
probably
ideas.
Not actually. Like, what?
No. Listen,
probably not.
What I'm saying is that definitely, probably not.
Definitely, probably not. I love it.
I'm saying these are just things that you can think about and hypothesize and be like, what if? And a lot of people, I saw the worst TikTok I've ever seen in my entire life. This guy was saying that the superstructures in our universe were starting to resemble the shape of a human, and I was cringing very hard because it obviously completely made up.
The universe has nothing to do with us. It doesn't care.
Yeah,
it doesn't care.
It's obviously completely made up. But
couldn't care less. Couldn't care less.
It was just hilarious to see how some people just like, you take like an interesting thing and everyone's like, oh my god, he's so smart. It's all made up, and what I just said before that, it's all made up, but it's things you can think about. Definitely think about, because I mean the whole concept, in my opinion, of a black hole forming is really, really cool. One thing we didn't talk about, I hate doing this, when we were talking about degeneracy pressure, I want to talk about just one fundamental thing: the Paulie exclusion principle. So degeneracy pressure is basically a thing because of the Paulie exclusion principle. So remember, as we were saying, so electrostatics repel these charges and keep it stationary. So electron repulsion, electron pressure, we can understand. But moving on to neutron degeneracy pressure, even as I was thinking about it, I'm like, I'm missing something.
why would they repel each other? Or why would they not, you know what I mean? Because there's no charge there. So the only reason they would repel or stay repelled is if there was a charge, if there was some kind of charge differential which caused it to move apart. However, here comes quantum mechanics. Wolfgang Paulie comes out with the Paulie exclusion principle, which basically, in average, I'll just summarize it. No two particles can occupy the same quantum state at the same time. Is a really easy way to think about it. Now, quantum state is a definable thing, which we're not going to do right now, which I'm not going to do right now. But if you want to think about it, you can just think about, oh, no two particles. It's very obvious to think about too if you just give it a second of a thought. No two particles can be in the same place at the same time, obviously, right? They can't be on top of each other. And that fundamental concept is literally what causes neutron stars to survive, right? And Paulie exclusion principle is a very fundamental concept in all of physics that basically allows these stars or these particular neutron stars to survive. And when it forms into a black hole, a lot of people start to question this particular principle. How does it still work if this thing is literally munched up altogether? Now, the way that works is interesting because in this particular black hole, what actually is happening, if you think about it, it's just gravity that's collapsing the core. So as these things are getting closer and closer together, in every black hole, this is not even a black hole thing, this is actually an Einstein thing, where he found that, or it's not an Einstein thing, but it was derived from his equations, that there's a certain distance, a certain radius, at which any object, after it is that particular distance, if the radius of that object is that particular number, depending on its mass, it will collapse into a black hole. Basically. Now, that is called a Schwarzschild radius. Very, very, very popular in black holes.
Why are you talking about this?
What do you mean?
The Schwarzschild radius.
No, because I wanted to mention the importance of, well, how does a star collapse into a black hole? Because the collapse only occurs if the star's radius, so as gravity is pushing it down, it collapses it until it reaches this radius. The moment it reaches that radius, everything inside collapses into a black hole. And everything on that radius itself freezes because time is frozen, because time is really weird in very heavy gravitational fields, right? And that's basically the black hole, right? That middle just falling in and the rest still working. And why I wanted to relate Paulie's exclusion principle to this is because even in a black hole, Paulie's exclusion principle is not broken. And the reason for that is actually because space is so warped inside of a black hole that technically the prediction still holds. So no two particles, even though they are actually crunched up literally in the same space, it's just that space is all curved and twirly and in all these different directions that you can't even think, right? So because of that, Paulie's exclusion principle still stands. I just wanted to bring up Paulie's exclusion principle before we ended it because that's a fundamental concept to how some of these stars even can resist the force of gravity. And it's how kind of black holes also start, right? I think we kind of ended it all the way, right? We went all the way from the basic small stars, what they would happen, and then we ended all the way on the massive star to the black hole, kind of completing that sequence.
For sure.
Right?
So yeah.
Anything else?
I think that's everything. Let us know if you enjoyed this episode. Make sure to follow us on Spotify, Google, YouTube, and any other place where you listen to this podcast.
Make sure to go on YouTube right now if you're not there already to check us out with the new merch. It's definitely going to be, as we mentioned in the future, we're definitely going to do something fun. And all the episodes are now going to be live. So I think I don't want to use the word vibe, but the vibe will be nicer. It'll be more uplit because we're now in person. So I think our episodes are going to definitely see an improvement. It's going to be a lot of fun. I'm so excited for this whole year.
100%. 100%. So this has been episode number 77 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.